Hey everyone, this is Hunter with Thrust Flight. We've got a really special video here for you today. We're doing something kind of unique. The video that you're about to watch is our exclusive content that we use in-house for training our multi-commercial add-on pilots. So this is something that we've never done before. We usually keep this in-house, but we really wanted to give back to the aviation community and, more importantly, help contribute to the safety culture in aviation. So we're hoping by providing this in-house content for free to everybody, we can accomplish those two things. So hope you enjoy the video and hope that it can make you a safer, better, more prepared pilot.
My name is Megan with Thrust Flight. Today we're going to be going through the multi-engine commercial add-on course and talking through the oral portion of the check ride. To begin, we have some new kind of bonus features with the multi, right? We have complex systems, maybe even high performance systems. The Seminole is not high performance, but that is something you could run into once you get your multi rating. We now have the constant speed propellers, which is part of the complex system. So we have to manage those. We have retractable gear, some effects and drag with the new complex systems and the retractable gear. Complex fuel systems really isn't too complicated, but there are definitely some differences from probably something you're used to. We have a little bit different environmental systems as far as cabin heat, cabin air, from just like a Cessna. Also, weight and balance and performance charts might look a bit different than something you're used to, so we're going to go through that together. Understanding engine temperature operations and how to control the temperatures and protect the engines as best we can to make sure they last a long time. Some advanced aerodynamics, so it's going to be a little bit more complicated now that we've got two engines on either side of the airplane. And definitely an increase in workload, increase in airspeed, increase in performance, power, things like that. So we have to really know how to stay ahead of the airplane now that we're in a little bit faster airplane with more to manage. So we'll start with a conventional multi-engine. The conventional multi-engine airplane, both propellers are going to rotate clockwise, from the pilot's point of view, that is. So we have something called a critical engine in this scenario. The critical engine is the engine that, if it has failed, it will most adversely, most negatively affect the performance and handling characteristics of the airplane. This is going to be the left engine, and we'll talk about how we determine that in a little bit. On the Seminole, we have counter-rotating propellers, so we don't have a critical engine. The aerodynamics of losing either engine are identical. So we do not have a conventional twin, and we do not have a critical engine. We have a counter-rotating airplane. So with the critical engine inoperative, both directional control and performance are going to suffer more so than when the critical engine is operating or when the non-critical engine is inoperative. So factors that are responsible for making the left engine critical, the way we are determining the left engine is in fact the critical engine, is this PAST acronym. So we have P factor, accelerated slipstream, spiraling slipstream, and torque. We're going to talk about each one of these. The factor or the impact from each of these, for P factor, it would be a yawing tendency. For accelerated slipstream, it would be a roll. Spiraling slipstream will again be yaw, and torque is going to be roll. And we're going to talk through each one of these. So with P factor, we talked about how it creates yaw. So we all remember from private, long time ago, that the downward descending blade on the right, as viewed from the pilot's perspective, creates a bigger bite of air, more thrust, more propulsion from the right side of that propeller. So we can see here the effects of that. So with the right engine, the center of thrust is shifted outwards towards that right blade, that downward descending bigger bite of air blade. So we can see the center of thrust has shifted outwards towards the right. Same thing for the left engine. But now if we look at this in relation to the center of gravity or the longitudinal axis, we can see that it's a much shorter arm on the left engine versus on the right engine. It's a much longer arm. So the longer arm means more momentum, more yawing tendency, more force to try to yaw us to the left. So with the left engine operating, we have less of a yawing tendency than we do with the right engine, which is why it's the critical engine on a conventional twin. Next would be accelerated slipstream. Again, this kind of all stems from P factor. So we see here again that we just talked about the center of thrust is shifted more towards the right side. In this picture, we're looking front on, but if we're looking at the back of the airplane, it's shifted to the right side of that propeller because that downward descending blade, we just talked about P factor. So that's what's happening here. But now we know that with more thrust, we have more backwards like airflow behind the propeller, right? We have more fast airflow behind the center of thrust. So behind that right side of the propeller there. And with this faster airflow, we have more lift. So I like to think about this with a steep turn. Like if we're turning, we know that the outside wing has to go farther, has to go cover more ground. So it actually goes faster through the air, creating more lift, and we have that overbanking tendency. So I like to apply that in this scenario as well, because we know that with more airflow over the wings, we have more lift, meaning more roll. So we see, again, similar to with P factor, as the left engine is operating, the right center of thrust is shifted towards the right side of that propeller. And then we have the faster airflow over that side behind the propeller here. So behind, kind of more like the inboard side of that wing. Whereas here on the right engine, it's shifted quite a bit outwards on that wing, maybe only almost halfway down the wing. So the arm is much longer on the right, from the right engine center of thrust to the longitudinal axis than it is on the left engine. Again, this tells us that the left engine would be the critical engine with the conventional twin. So building off of what we just learned, P factor and accelerated slipstream, we now have spiraling slipstream. This is also going to create yaw. So we have another picture here that tells us the direction that they go, and we'll talk about how we know that. So we just looked at P factor. Again, we've got the more thrust shifted towards the right side of that propeller blade on each engine because they're both rotating clockwise. So now that we've got that faster moving air we just learned about from accelerated slipstream, this is all building on top of each other. And with that faster moving air on the right, behind the right propeller, we have a lower pressure, right? We learned about in private Bernoulli's principle. So with Bernoulli's principle, he says as the velocity of the fluid, in this case it's just the air, as the velocity increases, the pressure is going to decrease, right? So behind the right side of that blade, we have a lower pressure, and then behind the left side of the blade, we have a higher pressure. Same for both sides of the engines. So we know that air always flows from high to low pressure. So we can see that this slipstream is going to kind of start to turn towards that lower pressure from high to low, and it's going to kind of spiral off into space here. Now with the right engine operating, it doesn't really help us. It doesn't hurt us, but it doesn't help us either. With the left engine operating, that slipstream is going to go directly towards the rudder, which one gives us more control of the rudder, right? More airflow over the rudder means more control of that control surface. But it also kind of pushes on the rudder towards the right, yawing the airplane to the left, which is now opposing the asymmetrical thrust. And then lastly is torque. So this one I like to look at straight from the front or back of the airplane. We have Newton's third law, right? So Newton said that for every action, there's an equal and opposite reaction. So with the clockwise rotating propellers, we have that right roll. So you can see here that the propellers, if we're looking from behind, they're rotating towards the right. So the opposite reaction is going to be that roll to the left. And that's actually going to oppose asymmetrical thrust with the left engine. So with the right engine operating, it actually is going to work in conjunction with asymmetrical thrust, which we'll look at in a second. But it's going to make things worse. It's going to make it harder for us to oppose that asymmetrical thrust, harder for us to stop the airplane from trying to roll us over. All right, so let's look at that and some kind of like break it down a little bit more. All right, so I'm gonna draw two airplanes here. All right, so we're talking about the P factor asymmetric race. Okay, so we're gonna break down past now. So I draw two airplanes here. This would be the critical situation where we have the left engine no longer operating, and then this is the non-critical engine. It has failed, the right engine has failed. So in either one of these situations, we have asymmetrical thrust. So the asymmetrical thrust is going to go towards the bad engine because that airplane now has asymmetrical thrust, right? We've got thrust on the right side, but not on the left side, and the opposite over here. So now I've got that working engine trying to go forward through the air, but it's turning the airplane towards the bad engine. So with P factor, as we start with P factor, we just talked about how that's not a very good color, how there's more thrust from that downward descending blade, right? So we have that downward descending blade creating more thrust, which pushes the center of thrust kind of more towards that right blade, kind of in that region there. So then if we look at the distance from the center of thrust to the longitudinal axis, we can see that with the left engine operating, it's much shorter than with the left engine failed. So that makes this the critical engine. Now, if we go on to talk about accelerated slipstream, we can just start from this point of view, right? So we've got P factor, we've already talked about that. We know that there's more thrust from that right side of the propeller blade, but now we've got that faster moving air behind it. So with that faster moving air, we have more lift on the right side of that propeller blade, behind that propeller blade. So over the wing here, farther out from the longitudinal axis here, I've got much more lift because I have faster moving air, I have more momentum to try to roll me than I do with the left engine operating. We can see that arm is much greater. So we use rudder to oppose all of this, right? We'll pick this color. That's not very good either. Maybe purple. So rudder is how we're going to oppose these turning tendencies. All right, so now we've talked about past P factor, accelerated slipstream. Now S is spiraling slipstream. So we just discussed that we know there's a lower pressure behind the right downward descending blade. Faster moving air, Bernoulli told us himself that faster velocity increases, pressure decreases. So faster moving air has a lower pressure. So from that we know the air is going to go from high to low, and so it's going to spiral in this direction, which we just saw that the left engine is critical because it had benefits from this spiraling slipstream. It gives us more authority with the rudder, gives us more ability to oppose that asymmetrical thrust versus here where it doesn't really help us, but it doesn't really hurt us either. It's just not as beneficial as with that left engine, that critical engine operating. So it all kind of stems off of P factor. So let's go ahead and talk about torque. I'll draw these down here. We'll draw the same scenarios, but I'm going to draw this from the back of the airplane, as if we're standing behind the airplane or we're sitting in the pilot seat looking out front. So here's our two scenarios. We've got the critical engine inoperative and the critical engine working. And we know that accelerated or asymmetrical thrust is always going to try to want to yaw us and roll us towards the inoperative engine. So here we've got the asymmetrical thrust. Of course, we've got our rudder working with us as well. And from Newton's third law, he told us that for every action, there's an equal and opposite reaction. So we know just looking behind the airplane that the propeller is going to rotate to the right clockwise. So what's the opposite reaction? That opposite reaction is going to be roll to the left, right? So we've got the opposite reaction going this way. All right, so let's take a look at this. Now we can see that the torque here, this is our torque, is going in the same direction as asymmetrical thrust. That's not very beneficial to us at all, right? We're going to run out of rudder authority much sooner in this scenario with our critical engine inoperative than we would with the critical engine working, because look over here, now torque and rudder are moving in the same direction. So it's going to be much easier for us to oppose that asymmetrical thrust in this scenario than here, where it actually adds to the severity of the asymmetrical thrust. So there we've got past. So all of those help us explain that the left engine is the critical engine. All right, so quickly, part 23. This is the part that explains determining airworthiness standards and certifications. So when a new airplane is built, they have to go through a number of processes to get the aircraft airworthy and certified for flight. So part 23 is going to tell us that airplanes weighing 19,000 pounds or less with 19 or fewer passenger seats, which is definitely where we fall. We fall in that category. So part 23 is going to tell us about airworthiness standards and certification. So when a new aircraft is built and manufactured, they have to go through several steps to get it airworthy and certified for flight. So aircraft 6,000 pounds or less with a VSO of 61 knots or less, which is the category that we fall into with the Piper Seminole, they're not required to climb or maintain altitude with the loss of an engine. So if we lose an engine, there's no certification standard that we have to maintain altitude or be able to climb. Aircraft more than 6,000 pounds with a weight or VSO more than 61 knots, they are required to maintain a single engine rate of climb. So they've lost an engine and they're required to maintain a rate of climb of at least 5,000 feet per minute at mean sea level, or at least 0.027 times VSO squared. So for twins certified on February 4th, 1991 or after, the single engine climb is expressed in terms of climb gradient. What does that mean? A climb gradient is the actual measure of altitude per 100 feet of distance traveled, of horizontal feet traveled, expressed in a percentage. So in this example, we can see this is straight out of part 23. An altitude gain of 1.5 feet per 100 feet of travel is 1.5%. So that's that climb gradient required for these heavier, bigger aircraft types certified after 1991. We do not fall into that category. We are up here in the bold section. We are less than 6,000 pounds. We have less than a VSO of 61 knots. So we're not required to maintain a climb or altitude at all. All right, let's talk about some V speeds. So we have our known V speeds that we've come to love: VR, VSO, VS1, VNE, VX, VX, VY, VNO, VNE, all those that we already are familiar with. But then we have multiple additional ones because we have the scenarios where we might only have one engine operating. We need to know our speeds to expect best glide, best climb rates based on only one engine operating. So VR is going to be 45 knots. These are all speeds for the Piper Seminole. VSO is 55 and VS1 is 57. So those are very, very close together there. VY, you've got 88. That's going to be blue line. Blue line is actually VYSE, but in our scenario, they're exactly the same number. So they're both 88 knots. So that's going to fall right there on that blue line on the airspeed indicator, which we'll talk about in a second. VX is 82, VA at maximum gross weight, so at 3,800 pounds, it's 135 knots. VFE, so flaps range for all flaps, is 111 knots. VNO is 169, and VNE is 202. All right, so now let's talk about some V speeds. We have the ones we're familiar with, like VR, VNE, VX, VY, VA, all those. But then we've got some additional ones. Since we have two engines, and then we also have retractable gear and things like that, we need to have different V speeds for the more complex airplanes. So these are specifically for the Seminole, the Piper Seminole. We have a rotation speed of 75 knots. VSO is 55 and VS1 is 57. Those are very close together there. VY is 88, VX 82. VA 135, that's going to be at maximum gross weight of 3,800 pounds. VFE for all degrees of flaps is 111 knots. VNO is 169 and VNE is 202. All right, so now let's look at the additional airspeeds we have. These are going to be for retractable landing gear and for single engine operations. So we have VMC at the very top there. It's 56 knots for the Seminole, which if we look back on the left side, we can see that it's right in between that 55 and 57. So right on top of our stall speeds there. So VMC is defined as the minimum controllable airspeed. So anything lower than this, we would not be able to maintain control of the airplane with the critical engine inoperative. This is going to be depicted on your airspeed indicator with a red line. It's going to be a red line right at 56 knots. Next is VYSE. This is 88 knots. So this is VY with a single engine. Same exact airspeed as VY, which makes it really easy for us to remember. And this will be depicted on the airspeed indicator with a blue line. VXSE, so VX, single engine, is going to be 82 knots again. And then we have this VSSE. This is definitely a new one. This is minimum single engine safe speed. So your MEI or your DP would never intentionally fail an engine below this airspeed. It's going to be 82 knots again, so same as VX. Then we've got two landing gear speeds. So LE, VLE here, this is landing gear extended or extension speed. So we can fly with the landing gear extended below 140 knots, and we can extend landing gear below 140 knots. VLR is retraction speed. So I have to be below 109 knots to actually retract the gear. All right, so let's go back to this VMC. So this is a new one, right? This is something we're not familiar with a single engine. So this is the minimum slowest airspeed where we can still maintain directional control with the critical engine inoperative. It is dependent on that critical engine So this is marked by the red line like we talked about. Directional control is more affected by airspeed. So the faster we are, the farther away we are from VMC, the more authority we have with the controls, right? We know that from just basic slow flight. The slower we get, the bigger inputs we need on those controls. Same thing happens with the rudder. So we get slow, and eventually I'm going to run out of rudder. I'm not going to be able to push on the rudder anymore to maintain control of the airplane. So this is going to help us resist those asymmetrical thrusts, those yawing and rolling tendencies with our rudder, and of course the aileron as well. This is a number we never want to reach. We don't want to be that slow. We don't want to VMC roll. We want to stay the heck away from this speed, right? We want to be safe. So we do a demonstration in the multi-engine course where you approach this speed to demonstrate the proper procedures for recovering it. But in real life, we want to stay as far away from this speed on a normal flight as possible. This is a fixed airspeed, and it's based on a set of circumstances, and we'll go into those circumstances for which the manufacturer tested it. So here is our acronym. We use the acronym custom FAM. You can see on the far right there. That's how we're going to remember that set of circumstances that the manufacturer uses to test the airplane. So this is defined by the FAA, but then tested by the manufacturer. So number one is C. So we've got the critical engine inoperative and windmilling. So we've got the left engine, the critical engine. It's inoperative, it's not feathered, but it is windmilling. So it's creating a lot of drag, which is not great. So it says left engine is inoperative and not feathered. That's a worst case scenario, right? We've got U is up to 5 degrees of bank and 0 side slip. So that's how we're gonna maintain directional control with one engine inoperative. So if I lose my left engine, I'm gonna raise the dead, I'm gonna bank into the right engine by about 5 degrees of bank, and I'm using 0 side slip, which is gonna be splitting the ball towards the right, and we'll see what that looks like in a moment. So it's going to be a forward slip, so we have a little bit of rudder towards the right and a little bit of bank towards the right, and that aligns the longitudinal axis of the airplane with the relative wind, which again is going to reduce the drag, right? It's going to help me maintain directional control, maintain control of the airplane. S is going to be standard day at sea level pressure, so remember sea level pressure and standard day is going to be 15 degrees, 0 feet. So this is talking about the conditions outside that they were tested in. Similarly to all the other performance charts you've probably seen, they were tested at standard day as well. T is trimmed for takeoff. This is set for neutral. So this is the condition that the airplane would have been configured in when the manufacturer tested it. O is out of ground effect. So when we're out of ground effect, we have an increase in induced drag, right? So we enter ground effect, the induced drag decreases, and we actually have better performance. So again, this is going to be a worst case scenario. I've just increased my induced drag, I've decreased my stability because I've climbed out of that ground effect. M is going to be max power on the operating engine. So we've lost our left engine, we're going to go full power on the right because I want to get as much power as I can because I've just lost half of my power, I've lost half of my thrust. That's going to dramatically decrease my performance. So I want to go max power on the operating engine. This next one is important. It's flaps at takeoff and gear up. It's not flaps up and gear up, it's flaps at takeoff and gear up. So remember that. With our gear down, that increases controllability, increases stability. If you guys have ever seen the keel of a boat, it's this little fin that sticks down below a boat, helps it stabilize as the waters are rocking around. That's exactly what gear does. It creates more stability for the airplane. So with the gear up, now I've lost that stability, and flaps at takeoff in our case would be flap 0, but for manufacturing purposes it's tested with flaps at takeoff setting. A is aft CG, so we know that we get more performance out of this, but we're actually going to have a shorter arm from the rudder to the CG, which is going to create a less effective rudder. And then M is going to be most unfavorable weight. The Seminole was tested with the most unfavorable weight, which would be a lighter weight, and this has the least momentum because it is a lighter weight. All right, so now let's talk about how each one of these factors affects our performance and our VMC speed, if we reach VMC sooner or later. So number one, critical engine inoperative and windmilling. So if we think about this, we know our performance goes down because we've got more drag, right? We've got more drag on that left side. The critical engine has stopped working. It's windmilling. It's basically a big disc sitting out there creating lots of drag as it spins. And the performance is going to go down and VMC is going to go up. That means I'm going to reach VMC speed sooner than that 56 knots. That 56 knots is what was published. And that's because if you think about sitting in the pilot seat here, we've got the right engine working and the left engine inoperative. So that left engine is not creating any thrust. So the only thrust I have is on the right side. It's trying to yaw me and roll me to the left. And now I added to the amount of drag that I have on the left side. So that's just going to increase that yawing and rolling tendency. And I'm going to run out of authority with that rudder. I'm going to run out of authority with the ailerons sooner than 56 knots. So my VMC speed is going to go up. Number 2 is up to 5 degrees of bank and 0 side slip. This is going to increase my performance, right? So I've just decreased my drag by aligning myself with that relative wind. So the performance is actually going to get better because now I'm trying to maintain that directional control. And my VMC speed is going to go down because now I've maintained directional control. I've got less drag on the airframe, less a relative wind hitting the side of the fuselage. I'm aligning myself with that relative wind. I have better performance. I have better controllability. And my VMC speed is going to go down, so I'm going to be able to maintain control longer before reaching VMC. Standard day at sea level pressure, my performance will go up because this is speaking of a lower density altitude, right? So I've got thicker air. I have molecules are closer together, so I create more thrust. My wings are more efficient. The propeller is more efficient going through that thicker air, so my performance goes up. With more performance, I've got my right engine working, and it's much stronger today because it's a low density altitude, so it's creating more thrust, more asymmetrical thrust, more yaw roll towards the bad engine. So that's actually going to make it harder for me to maintain directional control as long as possible. So my VMC speed is going to go up. I'm going to reach it sooner because now I've got more power trying to take over and yaw and roll me towards the left. Trimmed for takeoff, we put little X's through here because this is basically just a condition in which the manufacturer tested the airframe. So we know that it's neutral, right? We wouldn't have it in some dramatic up or down scenario. It would just be neutral, so it should be relatively flat and flush with the elevator there. So it's really not going to affect us. It's going to be so negligible that we don't even really need to talk about it. Out of ground effect, we talked about that keel effect, right? So I've got more stability in ground effect. We have less induced drag. So of course, my performance is going to go down as soon as I climb out of ground effect. So in ground effect, my performance is better, but as soon as I leave ground effect, my performance goes down. My VMC speed also goes up because I've lost that stability. I've got more drag, or I've got more induced drag, and my stability goes down, so I'm going to reach VMC sooner. Max power on an operating engine. So similarly to with standard day, our performance goes up because now I've got the most performance, the most power I possibly can. I've lost a lot of performance, right? But in this scenario, my performance is going to go up because I just went full throttle. Now I have more ability to maybe climb, maybe maintain altitude. But my VMC speed is also going to go up because, like we saw with standard day, more power means more yaw, more roll towards that bad engine. Flaps at takeoff and gear up. So with flaps at takeoff, in our case, they'd be 0, and gear up, we don't have that keel effect, we don't have that stability, they are up. So our performance goes up because we have less drag, right? We don't have any flaps, we don't have any gear, that creates less drag for us, better performance. But our VMC speed is going to increase because of that loss of stability, that keel effect no longer helps us out anymore because the gear is up. A is going to be aft CG. So with an aft CG, the distance from the rudder to the aft CG location is going to be much shorter than if the CG was focused more forward on the airframe. So performance is going to go up. We know that basic concept from private or commercial. We get better performance effect, faster airspeed, less fuel burn, more range with that aft CG. But VMC speed is going to increase, unfortunately, because we have a shorter arm from that rudder to that CG. So I'm going to run out of authority with that rudder sooner. And lastly, most unfavorable weight. Performance is going to go up because now I'm lighter. I don't have to create as much lift, right? The airplane doesn't have to work as hard to keep the airplane in the air with a lighter weight. But my VMC speed is going to go up because this has the least momentum. And I like to think about this in terms of the horizontal and vertical components of lift. So if I erase this real quick, and then we look at an airplane in these two scenarios. So we've got an airplane straight and level. We know that we've got lift, and we've got weight. And same thing in this scenario. We've got weight, and we've got lift, but it kind of goes off to the side, and then it breaks into those two components, the horizontal component of lift and the vertical component of lift, right? So this is our scenario. We're lighter. We have the horizontal component of lift, the vertical component of lift. In this case, we're raising the dead. So this is our dead engine, and this engine's still working. So the asymmetrical thrust is going this way. It's going towards that bad engine. Right, so we've got the asymmetrical thrust. So if I'm in this scenario and I increase my weight, so I'm a heavier weight, maybe even max gross weight, I have to increase the lift, right? I need to maybe increase the angle of attack, increase airspeed somehow. I have to oppose that weight to maintain level flight. So same thing happens over here. My weight increases, my lift must also increase. So with that increase in lift, you can see how the horizontal component of lift is actually going in the opposite direction of the asymmetrical thrust up here. So with more horizontal component of lift, I have more opposing forces for the asymmetrical thrust to help me fight that. But in our scenario, we just said that VMC goes up because I don't have this additional weight. I don't have this additional horizontal lift. I don't have that additional opposing force. All right, continuing on with VMC, we just looked at how it can change based on the configuration of the aircraft, flaps, gear, the conditions of the day, pressure, altitude, density, altitude, temperature, all of that. So it says at 5,000 feet, here's a scenario question. With engine failed, what will that do to VMC? So we're at 5,000 feet, we're at a fairly high altitude, we're at high density altitude. How's that gonna affect VMC? And if we go back to our chart here, we saw that standard day at sea level pressure, so like a lower density altitude, it's gonna have VMC increases. So now we're at 5,000 feet, a little bit higher than sea level, right? The VMC is gonna go down because we have less performance, less power out of that operating engine. So I have less of a tendency to yaw and roll me towards the bad engine. Aircraft manufacturers must limit the amount of rudder used to oppose the asymmetrical thrust to 150 pounds. That sounds like a lot, but that's what the maximum rudder pressure is. Then we've got something called the critical density altitude, and that's what this last piece is talking about. So the density altitude where VMC speed and stall speed are equal is called this critical density altitude. So essentially, if we're flying along at this altitude and VMC and stall speed are the same, we'll reach them at the same time. That's not gonna be a good day, right? We're gonna lose control of the airplane. It's stalling. Those are two very bad things that we want to avoid. So this can be really, really dangerous, right? And this should be avoided, which is why it's important for us to know the performance charts and to do them every time we fly, to know what to expect from the airplane. All right, speaking of performance, we've got something called accelerate, stop, and go distances. These are new. We do not have an accelerate go distance for the Seminole. We only have an accelerate stop distance. It is a performance chart that we'll look at, but the definitions are listed here. So accelerate stop distance is the total distance that it takes for us to go from stopped point on the runway, full power, we accelerate to VR, we're ready to rotate, but then all of a sudden we experience an engine failure. And then we abort the takeoff and bring the plane to a stop. So it's the distance from start to stop. We've added full power, reached VR, experienced engine failure, and come to a stop. Accelerate go distance is the same with additional twist at the end. So it's the total distance, again, from start, we accelerate to VR, we experience an engine failure, but then instead of aborting the takeoff, we continue the takeoff and climb to 50 feet. Kind of a little something for you to think about is when would you use an accelerate stop versus accelerate go distance? In what scenario, not in the Seminole, but in what scenario can you think of that you would abort a takeoff versus continuing to climb over 50 feet? All right, single engine performance. So we must have an idea of what to expect from the airplane, right? We have to know each day's performance abilities to be able to safely fly in each phase of flight. So we talked about how we lose performance with one engine inoperative, right? We've just lost 50% of the power, but the hit to performance is incredibly huge. It's 80 to 90% or even more a loss of performance. So that's big, right? My climb speed and my climb performance is going to go down dramatically. I might not be able to hold altitude. It's going to be much harder for me to control the airplane than it would be with two engines operating. And then, of course, with one engine inoperative, we have a harder time controlling because of that asymmetrical thrust. So now our performance is dependent on our airspeed, the drag, the gear flaps, the power, the amount of power, and of course the weight that I took off with. All right, so zero side slip, we saw this term earlier, and so now this is what it's going to look like in our airplane. So it's a little bit cut off, but we can kind of see how this is 0 degrees here, and then that 5 degrees of bank is between 0 and 10. So we've got a very slight amount of bank towards the working engine. In this case, it's the left engine has failed, and the right engine is working. So we're banking towards the good engine. We're raising the dead, as they say, raising that dead engine. And we've split the ball, so that literally means to split it in half with that line there. So splitting the ball down the middle to create that zero side slip, align the fuselage or the longitudinal axis with that relative wind. This is going to give us better aircraft performance. Again, we have a horizontal component of lift helping us oppose asymmetrical thrust. Now that we've got a slight amount of bank there, we're splitting that lift into horizontal and vertical components. And then this is going to minimize drag as well. Like we talked about, less relative wind. We're not kind of slipping through the air like this. Now we're aligning ourselves with relative wind, and we don't have that additional drag. Similarly, we want to reduce the drag with the propeller, right? We don't want this windmilling propeller. This creates a huge amount of drag compared to the feathered position. So with it windmilling, it's actually much, much worse than with it feathered, and you'll feel that performance effect when you get to fly the airplanes. So this windmilling propeller actually looks like a disc, and it's creating drag for that whole 360-degree turn, whereas we have the two scenarios here with the stationary feathered or unfeathered propeller, so it's a little bit thicker, right? Creates more space, more plane for that relative wind to create drag with than this one does. It's much skinnier. There's less wheel estate, I guess I'm trying to say, for that relative wind to create drag with. So this is why we want that engine feathered. It's going to be much easier for us to maintain control of the airplane. VMC is going to go down, right? We talked about how with the critical engine inoperative and windmilling, the VMC goes up, but with it feathered, it's going to go down. Less drag, less tendency to turn and yaw and roll me to the bad engine. So it says VMC is the highest when the critical engine is inoperative and windmilling. All right, continuing on with performance, we've got ceilings. This is talking about both two engine ceilings and single engine ceilings. We have both an absolute and a service ceiling. So an all engine ceiling, so both engines are working. Service ceiling is the highest altitude at which the airplane can maintain a climb of 100 feet per minute. It's reached its absolute ceiling when there's no longer a climb possible. So a service ceiling, both engines working, I can still maintain a climb of 100 feet per minute. An absolute ceiling, I can no longer climb. Single engine service ceiling, so I've lost half of my power, I've lost half of my climb. So single engine service ceiling is only 50 feet per minute climb, while the absolute ceiling is still no climb possible, but this is all single engine. The unavoidable drift when we reach our service ceiling is called drift down. So VYSE, that blue line, I'm sure you'll hear your instructors say multiple times, don't get below blue line, keep it above blue line, don't get below blue line, keep that blue line. You're gonna hear that a lot, and that's because of this drift down. So VYSE is kind of a bonus VG, or best glide speed. So if I lose my engine above the single engine service ceiling, let's say I'm flying along at like 7,000 feet, and I've calculated my service ceiling is 4,000, I'm not going to maintain 7,000, right? It's impossible. I can't do it with half the power, with 90% less performance. So I'm going to drift down. I'm eventually going to kind of sink towards my service ceiling. So the distance is affected by speed, just like when you lose your engine in a single engine Cessna, right? So if I hold VYSE, or best glide, I'm going to go the farthest distance for the amount of altitude that I lose as I drift down. So it's kind of a little bonus feature there. But that's why you're going to hear, don't get below blue line. All right, so now we're getting in the airplane. We're ready to taxi and taxi out to the runway using our braking. So we want to talk a little bit about how to kind of do this now that we've got a different thrust going on each side of the airplane. So we've got asymmetrical thrust, or differential thrust, you'll hear it called. You can use while taxiing. This should really kind of be the last resort. We do have a steerable nose wheel, so please use the rudders first. If that's not working, you have toe brakes that you can use. And if that's still not working, then you do have asymmetrical thrust. So you can use the outside engine, the outboard engine. So if I'm turning to the right, I'd use that left engine to help yaw me, help turn me towards the right. We always want to avoid tight turns though. We want those wide, swoopy turns, right? We don't want to pop a tire. I don't want to have to tell my boss, or I don't want to have to tell, the next student that's expecting their check ride to be tomorrow that we just popped a tire. So, make sure we're doing those wide, swooping turns. We apply rudders for turning and reducing throttles before braking. So we wouldn't use the brake and the gas in your car at the same time. So you can bring the throttles all the way to idle before braking. If you need to, like if you're going really quickly down the taxiway, or just before bringing it to a stop, really reduce those throttles to idle first. We talked about the toe brakes, just like your favorite Cessna 172s or Piper Archers. We also have hydraulic brakes on the main landing gear wheels. All right, so next we're going to go through performance. So that was kind of all the introduction, the asymmetrical thrust, the aerodynamics, and things like that, VMC, critical engine. Now we're going to go into performance. So there are multiple charts in the POH. There are quite a few. They all look kind of like what you've seen on written tests before. They have the temperature, pressure, weight, wind, and then you've got like an example. So you can see here they've put an example on here, and at the top corner there's the example temperatures, pressures, weights, winds, and everything that they've used to show you this example. So you can follow that to help you understand how to use these performance charts. So like in this example, this is our short field accelerate and stop distance. So remember, accelerate stop distance is the distance required. So we've got our distance along the side here that it takes for us to add full power, reach VR, experience an engine failure, and come to a stop on the runway. So that's going to be quite a long ways, you would think. It would take us a little bit to get to VR and then to get to a stop. So it's going to be a longer distance. So in our example here, they said it's 8 degrees Celsius, so they entered the chart here at 8 degrees. When you're doing these charts, please make sure you know the units between each number. They're not identical from chart to chart. They don't transfer perfectly. So the units between here might be different on the next chart that we look at. So here we've got 8 degrees. Went straight up to our pressure altitude of about 680 feet there, so just below sea level, just above sea level, below 1,000 feet. We come over to this reference line. So we go straight over to this reference line. Our weight that day is 3430. So we've got 3,500, it looks like right here. And so we've followed the line down towards 3430. Again, we've got this reference line, so we just come straight over. Our wind component is 5 knots of wind that day, so 5 knots here. Followed the lines, kind of paralleled them down towards 5, and again straight over to get our accelerate stop distance about 1,750 feet. So we're going to make sure we want to calculate that so that we know what length of runways that we can go into based on the outside temperatures and conditions and weights of the aircraft. So just going through the POH, we've got our takeoff, roll, short field effort. So no longer accelerate stop distance. This is just our takeoff, roll for a short field. So the numbers are going to be a little bit shorter or a little bit smaller over here. You can see how much the units have spread out over here. So just be careful when you're doing those. So similarly to the chart we just looked at, we've got an example in the corner. We would start with the outside air temperature, move up to pressure, altitude, over to the reference line, follow the lines proportionally down to the weight, straight over to the reference line, correct for the winds, and then find our short field takeoff roll distance. Some things I want to point out in these two charts. So that one was the takeoff roll distance. This is the short field takeoff over 50 feet. So very similar, but two different distances there. Again, it's performed the same way, temperature, pressure, altitude, weight, and wind. A couple things you'll notice in here. It's a little bit hard to see, but when you look on the POH, you'll notice there's this triangle right here. It's kind of shaded in. And it tells us up here in the caution box, it says if you're in this shaded region, the best one engine inoperative rate. So we have one engine inoperative, and our rate of climb is going to be less than 50 feet per minute if the takeoff weight is in the shaded area. So that's something we need to know, right? That's going to be pretty bad performance. So they shaded in that region there for us. Moving through the POH, we come to climb performance, both engines operating gear down. So we have a gear down and a gear up. We've got two different charts here, done exactly the same way. We've got our example up here in the corner. So we've got our temperatures down at the bottom, very similar to the last chart we looked at. So we've got 8 degrees Celsius. Come up here to our pressure altitude. And instead of going to a reference line, we just go straight over to our weight and then straight down. And that tells us our rate of climb in feet per minute with gear down. And same thing with the next chart, gear up. So we'd come over to our weight and straight down to find our rate of climb. Look at that, 1505 feet per minute. That's pretty great, right? Then I go to climb performance, one engine operating, gear up. Climb rate's now 285. That's a huge hit, right? So that's really important to know these things. But this one is very similar to the ones we just looked at. So climb performance with one engine operating, gear up. Hopefully we wouldn't have the gear down unless we're coming into land to reduce that drag. So same thing, temperature, sea level, pressure, or pressure altitude, straight over to the weight and straight down for rate of climb. There's one thing I want to talk about with this performance chart specifically. If you download the PA44 app, you'll notice this chart here and with the colors here. And this actually shows us our service and absolute ceilings. We can kind of work backwards in this chart to find those. There's no single engine service ceiling chart, so we kind of have to go backwards to figure it out. So we know our rate of climb, right? We know our feet per minute. For the service ceiling, it should be 50 feet for a single engine. And this is straight off the single engine gear up performance chart. So we have 50 feet right here, and we know our absolute ceiling is 0. So we know that already. So we're going to work backwards to find the altitude. So in 50 feet per minute for the service ceiling, we go up towards our weight. That's another known thing. We know our weight. So we go up to the weight and straight across. And we've written this line down here at 20 degrees Celsius. So we know the outside air temperature. The only thing we don't know in this chart is the altitude at which we're going to be at that service ceiling, right? So I'm going to plug in everything I do know. And then at the line where this blue line intersects my temperature right here of about 4,700 feet, that's my service ceiling. Same thing's done for the absolute ceiling. I start at 0 feet per minute because I know I can no longer climb at that altitude. I know my weight. I'm a little bit higher altitude, right? Because now I have no climb at all. So I've climbed above my service ceiling. So I go up to my weight, straight over to that temperature line, and now my absolute ceiling is about 5,600 feet. A little bit higher, but that's how we can kind of work backwards to find those numbers. Fuel time and distance to climb. This one is a little bit different. So we can see here that they've done some subtraction in their example. Because this is the time, fuel, and distance it takes for us to climb from whatever altitude we depart at to the altitude we climb at. So we're not usually taking off perfectly at 0 feet MSL, right? Like at Addison, for example, the altitude is 645 feet. So we're going to climb from that altitude to our cruise altitude. So we're going to take the difference between those two altitudes there. So our example, we've got flaps up and about 8 degrees Celsius. So we enter same place we usually do with the temperature here. We go up to pressure altitude and then straight over, not to a reference line, but to these 3 different individual lines. So the first one here is fuel, the second one's time, and the last one's distance. So if I bring my line over here and hit the fuel line and go straight down, it's going to tell me it's about 0.4 gallons. It's kind of hard to see. It's all kind of compressed in here together, but they've come up with a number of about 0.4 gallons for the departure elevation. Then you can see a second example up here. So now at the elevation we've climbed to, it's -2 degrees Celsius. So we enter the chart at -2, up to our cruise altitude, straight over to fuel, and straight down. And they found about 2.8 gallons. So the difference there is about 2.6, and then 0.4 from the departure elevation. So about 2.2 gallons from departure to the elevation of cruise climb. And the same thing is done for time and distance. So you would come over to the time line, straight down, and distance line, and straight down, and then take the difference between those two numbers there. We've also got one for descent. So this looks a lot like the one we just saw with the climb rates and the fuel time and distance. So again, we've got that calculation up here from the numbers that they found based on the difference between their cruising altitude to their touchdown elevation altitude. So we've got the 2 examples here. It's a little bit easier to see in this example. They've come over to fuel, straight down, time, straight down, and distance, straight down. And then they've taken the difference between those numbers and the numbers for their destination elevation. All right, let's go back to the sky real quick. So speed, power, we've got another example, which is excellent. Tells us we're about -2 degrees Celsius. We enter same time, or same thing like always, outside air temperature, up to pressure altitude, straight over, and then we pick one of these lines. So if we're cruising at about 55% power, 65 or 75% power, we would stop at that point and go straight down to find our true airspeed. The dashed line versus the solid line is explained to us up here. It's economic cruise versus performance cruise. So depending on how we have the mixture leaned and our aircraft configured, we would choose either the dashed line or the solid line, and then go straight down from whatever our power setting's at to find our true airspeed. So based on our power, our speed, and we can get our speed. So that's what it means by speed power up there. So how do I know if I'm at 55, 65, or 70? I've got this lovely chart. So we have 3 sections here. It tells us in this box, 75% power, 65, and 55. These are throttle settings. So these are manifold pressure settings in the box. And up at the top, we have RPM settings. So we've got 22, 23, 24, and 2500 RPMs in this box here, for example. So if I'm cruising, the checklist says about 20 inches to 23 inches and 25 or 2300 RPM. So about 20, 23, and 2300, I can figure out where I fall in these boxes here. So let's say I'm cruising along at 20 inches and 2300. I'm perfectly in this box. I don't see 20 inches anywhere like really in here, right? So it's going to be 20 and 2300. It's going to fall in this box. That tells me I'm at 55% power. That's pretty normal. We usually cruise on the lower end because we're already going faster and things are happening faster. So we kind of cruise a little bit lower speed. So we're at 55% power, and it tells me my fuel flow. My fuel gallons per hour is 8.7 gallons per hour per engine. We could double that. FT means full throttle. So you're climbing along and you're trying to maintain your climb power settings, and eventually the air is going to get so thin that the air inside the cylinders is going to get thin, and you're not going to be able to maintain your climb power unless you're at full throttle, and still you might not be able to maintain that manifold pressure setting. So that's kind of how we use that chart there. Then we've got, similarly to the takeoff short field distance, we've got the landing distance over 50 feet and the landing distance ground roll short field. Done the same way, just the opposite manner. So instead of taking off, now we're landing. Okay, that's it for the performance charts. So that was a lot, right? But the more you look at it, the more it'll start to make sense. The more practice, the easier it is for you to be able to finish those. All right, so we've done our performance charts. We've looked at our performance that we're expecting for the day based on temperature, pressure, altitude, weight, wind, all that. And now we're ready to take off. So we get to the run-up area and we do our pre-takeoff briefing. It's gonna change a little bit because now I've got 2 engines and I've got landing gear, right? So if I lose an engine, it's not an immediate I have to land in front of me situation. I can just get in the pattern and come back and land, right? I've got 1 engine operating, I'm still flying an airplane. So my takeoff briefing is going to be a little different based on these situations, and then this is how it's kind of going to go. You can vary it slightly, but this is a very general takeoff briefing. So any abnormalities on the runway. This could be loss of directional control. Maybe I have a flat tire. Maybe I lost a brake. Maybe I have a loss of thrust, maybe one of my engines failed. For whatever reason, if it's not directional control, maybe I have a weird smell or a weird sound, or there's a coyote on the runway. For some reason, I'm gonna abort the takeoff, right? So I'm gonna pull both throttles to idle. I've got 2 of them there. I'm gonna pull both throttles to idle, probably apply the brakes and try to exit the runway. Pretty straightforward. Abnormalities after takeoff below TPA. This could be depending on where your gear is. If gear's down, land back on the runway if I've got runway remaining, right? If I don't have any runway remaining and my gear's already up, I'm gonna immediately go through my emergency flow, which needs to be memorized. That's that bold section and the engine and emergency section part of the checklists, and it says engine failure in flight. That's the emergency flow. I'm gonna go through that, I'm gonna feather it. I'm not gonna troubleshoot because I'm low, I might be close to buildings, I don't have a lot of altitude, I don't have a lot of time, right? So I'm gonna feather it, I'm gonna get back in the pattern and land on the runway I took off from. And then we've got abnormalities above TPA. So if we've got plenty of altitude, I've got a little bit more time to spend trying to get the engine restarted, I'm gonna go through the flow, but instead of feathering, I'm gonna troubleshoot it. If troubleshooting works, great. My engine's working, but I'm still coming back to the runway because I just lost an engine. So I'm coming back to land. I'm gonna have someone look at it, see if there was a problem with it. If it doesn't work, then I'm gonna secure it, I'm gonna feather it, and I'm gonna come back and land again. Both instances, like it says, you're returning to land. Don't continue on a long cross country if you just lost an engine. All right, climb to cruise. So we have kind of a cruise climb. Similarly, maybe in some of the single engines, if they tend to overheat in the summertime, or if you want better visibility over the nose, we usually use a cruise climb. So on advancing power, on a rotation or on the ground before rotation, we're gonna make sure everything's in the green. We're gonna, once we have reached VR, we're gonna rotate. You're gonna tap the brakes to stop them from spinning. So once they go up into the wheel wells, they're not still spinning. And you're gonna bring the gear up. So you're gonna pull that handle up. And we're gonna climb at blue line, which was 88 knots, plus 10. So about 100-ish knots there. This creates a safety margin between that blue line, that airspeed. In case you do lose an engine, you've got a little bit more speed there. And then we go into our cruise climb at 500 feet. So 500 feet above the ground, we're gonna pull our throttles back first to 25 inches, and then slowly reduce our RPMs, our prop settings to 2,500 RPM. This kind of referred to as 25 squared, because 25 inches and 2,500 RPM. This is the setting for max continuous power, and it's gonna be a little bit, shallower climb, a little bit easier on the engines, easier for us to see traffic over the nose also. We do have a cruise climb checklist and a cruise checklist. Once we get to cruise, we would then reduce the throttles to that 23 inches range and the props to 2,300. Then of course we've got more checklists, right? There's always a checklist. So we've got before landing checklist, and we have this memory acronym GUMPS that helps us remember everything on the before landing checklist. So G is not gear. A lot of people think GUMPS, G is gear. G is gas. So I'm checking between the seats, my fuel selectors are on, and my 2 fuel pumps are on. That's all kind of part of the gas. I've also got U for undercarriage. So instead of G is gear, we use undercarriage is U. So I'm gonna put them down once I'm below 140 knots. I'm gonna see those green lights turn on. I'm gonna say 3 green, 1 in the mirror. I'm gonna look outside. There's a little mirror on the side of the engine there that I can see the nose wheel, because I can't see the main wheels. They're under my wings. They're blocked by the wings. So I'm gonna look in the mirror to see that I do in fact have one of those geared down. M is gonna be mixture full rich. Props are gonna go full forward on final. So we're not gonna do anything with the props until final. You can sync them, like if you hear like a whoa, 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 whoa kind of noise, you can sync them, but they're not gonna go full forward until we're on final. And then S is making sure our seatbelts are secure and our switches or our lights are on. There is a checklist, and we do this multiple times in the pattern. I typically do it downwind, base, and final. That gives me 3 chances to verify that my gear is down. I do not want to gear up landing, right? That's expensive and it's embarrassing. So I don't want to gear up landing. So I'm going to check 3 times that my undercarriage is down, and that gives me a chance to recheck on final that my props go full forward. If I'm going to go around, I'm going to add full power, right? Full throttles. So if I'm going to add full throttles, my props better be full forward, or I could cause some serious stress on that engine. So that's going to give me another chance to make sure my props are full forward. All right, so we've done our GUMPS checklist. We're ready to land the airplane. We've got the pre-landing aircraft configuration. We've got flaps, we've got gear, we've got props. All these things are going to help change our drag, change our speeds, everything like that. Change our stability. Like we said, the landing gear acts as the keel of a boat, so it has that stability effect, and it lowers VMC, which is a good thing. We also need it down to land. Flaps are going to create more drag. They're going to slow down our speed because of that greater control surface deflecting the air, decreasing performance. We're going to use the landing gear to your advantage to slow down to get into that flap speed range. So we know that VFE is 111 and VLE is 140. So the landing gear extension speed is much higher than the flaps extension speed. So if I lower the gear, that's going to help me slow down to then be able to add flaps. So once I do that, then I'm going to set power and increase drag for landing. So when I put those props full forward, you're going to slow down quite a bit, and that's going to help you get down to more of an approach speed for landing. And of course, we're going to do that GUMPS 3 times, each leg of the pattern, to make sure our gear is down and our props are full forward, as well as seatbelt switches and mixtures. All right, so now we're going to get into systems. We're going to start with the gear horn versus the stall horn. So we have 2. We've got some safety equipment on board the aircraft because we have gear, and the manufacturer wanted to make sure we remembered to put the gear down. So we're used to the stall horn, right? It's a continuous beep. The gear horn is going to be more of a beep, 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 a segmented beep there. So you can tell the difference just by the sound of the noise that you're hearing. So the gear horn helps prevent us from unintentionally landing with the gear up. That would not be good. Just want to avoid that. So we have some safety measures, including the horn. If you hear the horn while doing normal maneuvers with the proper configuration, something's wrong. So don't ignore it, right? It's there for a reason. They didn't put that for fun. It's to help warn us that something is wrong. So if you hear it, maybe take a second to think, okay, why is it going off? What is it telling me? And we're going to check the POH for horn conditions. These are the ones straight out of the Seminole POH. So the gear horn is going to go off when these 3 things happen. It says the stall warning does not go off on the ground. So if you're on the ground and you hear a beep, it's not the stall horn. If you hear the gear horn, these are the 3 conditions in which it's going to start to sound. So if you reduce your throttles, either one, doesn't have to be both. It could be left or right or both. Below 14 inches of manifold pressure with the gear still up, it's going to start to beep. The airplane is sensing that you're lowering the power settings as if you're coming into land. So it's going to say, hey, your gear is still up. You need to do something about that. Additionally, flaps extended past 25 degrees with the gear up. Again, the airplane senses you're coming into land, so you've extended your flaps to the second notch or 25 degrees. With the gear up, it thinks you're coming into land, it's going to start to beep. And lastly, if accidentally maybe you bump the gear selector or somehow it gets moved into the up position while on the ground, it's going to beep. So it's going to say your gear position is in the wrong position, right? You're on the ground, your gear needs to be down, so it's in the wrong position, and it's going to warn you of that. Okay, so we kind of talked briefly about the emergency engine outflow. This is the engine failure in-flight emergency checklist. This is memory items. Pretty much up to the verify, that is the memory items. This is kind of like the conditional situation, but that is all the same. So the first thing I'm gonna do, I'm gonna maintain control of the airplane, right? I'm gonna maintain directional control, positive control of the airplane. I'm gonna make sure I'm pitching for at least blue line. I don't have to climb to get to blue line. I just don't wanna be any slower than blue line. So if I can hold my altitude, great, that's a good day. But if I can't, I don't wanna get any lower than blue line like we talked about. I'm gonna increase that 0 side slip, so 5 degrees of bank, splitting that ball towards the good engine. So I've maintained directional control, right? That's the first and foremost thing. If you go straight to mixtures full and you're not maintaining control of the airplane, that doesn't matter. You've gotta maintain control of the airplane. The rest is secondary. So then I'm gonna go mixtures full, props full, throttles full. So I'm gonna power up. I'm gonna put my whole throttle quadrant forward. Then I'm gonna clean up. So I'm gonna clean up my drag. So gear up, flaps up. I'm gonna then figure out which foot is dead, so I can tell which engine has failed based on which of my legs isn't really doing anything. So let's say my left engine failed. I'm banking and splitting the ball towards the right engine. I'm putting in some of that right rudder to stop me from turning towards the left too much. So now my left leg is just kind of hanging out, not really doing much. So my left leg is dead, my left engine is dead. So identify left leg, dead engine. And then verify by pulling the throttle back to idle. So maybe I've got it wrong. Maybe I think my left engine's dead, but really my right engine's dead. So I'm gonna reduce my throttle on the left side to idle to see if I have a change of control. If something changes, I start to yaw around, that's probably not the right engine. I need to check the situation. So then I verify by reducing the throttle on the dead engine, and then I figure out my situation. Am I below TPA? Am I above TPA? Do I have time for a checklist, or do I need to just come back and land? If I'm below TPA, I'm gonna continue to the secure checklist. It's gonna be feathering the engine. So I'm gonna pull that prop all the way back to feather. I'm gonna pull the mixture all the way back to idle cutoff. If I'm above TPA, I'm just gonna come back to my checklist. I'm gonna troubleshoot the engine, see if I can get it restarted, right? I don't wanna feather it, because if I feather it, I can't troubleshoot it. So I'm gonna troubleshoot it, I'm gonna follow my checklist. If I can get it restarted or not, either scenario, I'm coming back to the runway to land. And there is a checklist. These first several items are bold, they're memory items, but we do have a checklist for the rest of it. Here's the secure checklist. So let's say I'm above TPA and I want to troubleshoot it. So I've got my troubleshoot checklist on the left there. So my troubleshoot flow is going to go like this. I'm pulling out my checklist, maintaining control of the airplane. I'm going to start by throttle. I'm going to see if I can open it a little bit to silence the gear horn. I'm going to check my fuel pumps. I'm going to check my mags. I'm going to check my fuel selectors. The primers are locked. The carb heat. I'm going to see if maybe I just had a little bit of carb ice. If I turn that heat on, does that fix the problem? I'm going to check my fuel pressure, fuel quantity, fuel pressure, and then oil pressure and oil temperature. If the engine is still inoperative, so none of this worked, then I'm going to go to the secure checklist. But if some of that worked, great. The engine's working. Maybe I just forgot to turn my fuel pump on for takeoff, and now I can restart the engine and come back and land. If it doesn't work, here's my secure checklist. So we said we were going to, this is in the reverse order, we're going to reduce the propeller lever to full back. It's going to be in the feather, the full down position, and mixture to cut off on the inoperative engine. Then I'm going to secure the engine. So I'm going to turn off the fuel selectors, the fuel pumps, the mags, the alternator, the cowl flap. I'm going to close it. I'm going to trim out the airplane as required just to make sure I'm able to kind of easily fly the airplane. And then make sure my fresh air fan or fresh air blower is off. So when we're practicing these maneuvers, the POH has told us for VMC demos or intentional engine failures that we have to do this no lower than 4,000 feet above the ground. So if you're performing these maneuvers, this VMC demo or the engine shutdown, feather and restart, that's going to be above 4,000 feet above the ground. All right, now let's dive into some more of the nitty-gritty systems. So we talked a little bit about the landing gear emergency warning systems. So we've got to know our systems through the POH. So definitely take the time to sit down and read each page of the POH. It is maybe around 300 pages. It's quite a bit, but there's a lot of pictures. So that's a good thing. We've got performance charts and things like that.
All right, well, we hope you enjoyed that video. We've got a lot more coming like it, so please subscribe if you're interested. And if you or anyone you know is interested in becoming an airline pilot, please check out our Zero Time to Airline program.